say the current through the resistor was going this way, I think, left to right on the screen, right? We said it was going this way, like that. That was the opposite of what I should have said to you.
Yeah.
It's supposed to be arrow. My hand blocks. So we said yesterday was going this way. I misspoke. That's not correct. It's actually going the opposite way of that. I'll tell you why. So the actual current was going this way across the screen. I tested it 7-2. Current actually going from right to left there because it tells you that this is the more positive half of the resistor, so that's where the protons are coming from as they go through the resistor. That's what those labelings mean. So where the plus sign is telling you where the more positive part of the resistor is. That would be where the protons are coming from, and they're going to go towards the negative side of the resistor. That's not a battery though. That's why it's different. That's why I got myself confused yesterday. I was thinking it was a battery. But remember, they lose energy going through a resistor, so you would want to go backwards, so to speak, if that helps you. Keep it all the same. Yeah. And then so this one's also going down. So the answer is still 5. We said yesterday it was 5 going away. The answer would actually be 5 amps coming into the battery. But it's still 5 amps. Oh, because we said yesterday 6 over 2 is 3 amps, 10 over 5 was 2 amps. And so if there's 3 plus 2 going out, there has to be 5 coming into the junction. Okay, so all the math we did yesterday was perfectly correct. We all should have just been drawn the opposite of the direction. What's wrong?
I just don't get why they're going.
Why they're going out? Because this labeled here on this is the more positive half of the resistor, or the higher potential side of the resistor, and the protons go from the high potential down to the low potential. So the current's traveling this way.
Oh, that's not.
When it's gaining energy, it does. And then so we're going through, it's going to lose energy. So you can think of it as going through a battery backwards, if you want to draw a parallel. It gets pushed through by the stuff behind it. Yeah, I see. Push through. Okay. All right, let's look at it. Oh. 5 then. Got some math questions coming up here. Pretty exciting stuff. This was number 5. What are the questions? Question 5. The light bulb in this circuit diagram here has a resistance of 1 ohm. We can write that down. 1 ohm. And then we also know that what's the difference? Point A and B. That one, I thought this was a very odd way to read this question. We want to know what are the values of the change of potential between 1 and 2, 2 and 3, and 3 and 4. And then what about the voltage and move? So let's look at this question here. So can we right now tell the change of potential between, we need to find the change of potential across the resistor, across the light bulb, and from here to here. Can we do that as this problem is currently written or drawn without doing any extra work first?
No.
No. What do we need to find in order to do this problem? The current would be important for us to find. Because then we can go back and say V equals I. Ultimately, we want to try and use the Ohm's law, V equals I times R, to find the voltage across the resistor and the light bulb. But we don't know the current yet, so we can't quite do that. So we need to find the current, then we can do I times R here, I times R here. What should the sum of those two voltage drops add up to? So the total out of the battery. Okay? Questions about that so far? The this voltage drop here is going to be 0. There's no resistance in the wire. But the sum of this voltage drop and this voltage drop should add up to 3. I started with 3 out of the battery. And for series. So I'm going to use my loop rule in order to find the current. So I'm going to pretend I'm a what? Proton. Proton going around the loop. Which way do you think the current's going to be going?
Up, clockwise.
Clockwise. Very good. So it's going this way most likely. That's the way the battery is going to push those positive charges. So I'm going to go around. I'm going to cross that battery. I'm going to gain or lose energy. So gain, I'm going in the negative, out the positive. When I go out the positive, I'm going to gain energy. So I have just that voltage from the battery first. I'm going to cross that resistor. Am I going to gain or lose energy across the resistor? Lose energy. So I'm going to add a negative I times R right there, R1. Across the light bulb, I gain or lose energy. I can find that the same way I find everything else, I times R. I can do minus I times, I'll call that R2. And what's that whole thing have to equal? 0. So I'll add up to 0. Questions? It adds up all those different places where the voltage changes. I is the same in both because they're series circuit, but not a series circuit. I have to do a little more work for that. So now I can go through, do some math. Or this is going to be 3 volts. And then I'm going, I'm going to skip some steps here. So that's going to be over here. It's going to equal, I'm going to move this term to the right. So that's going to be 2 ohms times I plus 1 ohm times I. Right?
Yeah.
2 times I, 1 times I. There, so that's going to be what, 3I? Is that right?
Yeah.
So what's that? The R1 is 2, R2 is 1. So I combine those together, divide, and then my current's going to be 1 amp. Like that. Agreed? Did that right? Hopefully. Now I go back to my voltage drops. This one would be I times R here would be 1 times 2. So this one is going to take up 2 volts. 1 times 1 here will give me 1 volt. 2 plus 1 is 3. That's right. Question about how we did there. Okay, part B then says what happens when I remove that light bulb. So we'll use orange here. So this light bulb, goner. Okay, is there going to be a current in the circuit? No. Now there's going to be a huge hole in the circuit. This is like gone. There's going to be a huge gap here. Is what they're trying to tell you. There's a gap in the circuit now.
I thought it just meant the wire continues.
Yeah. I did not know that. So I was thoroughly confused. I just kind of guessed what I thought they wanted. Yeah. Question 5 says use delta VAB as something. You got me. I'm not sure what they're going for there. But anyways, now that bulb is gone, so there's not going to be any current flowing. So let's go. It's not quite as simple as you would think then for the answer. But let's go through this. There's no current flowing. So is this resistor going to take away any energy if there's no current flowing?
No.
No, it wouldn't actually. Good. So the potential at 1 and at 2, how do you think those would compare?
The same.
They'd be the same, but they're both going to be whatever the positive half of the battery is. And then how will 4 and 3 compare?
The same.
They'd be the same. They're both going to be the negative side. And so if you measured between these 2 places, which that would still be a 3 volt difference over there. But there wouldn't be a current flowing. I thought it was, again, kind of a weird question. That's 3 and 4. Since these are touching the negative side of the battery, this whole wire would still have there'd be nothing moving, but it would still have a negative potential. But there's nothing flowing on it. And same with the top wire, this whole wire would have a positive potential because it's touching the positive side of the battery. And so if there's a big hole here, just if you were to measure or just subtract that from that, you still get 3 volts. I don't know. Next year, if I won't have time, 5 volts. I don't know about that. But I want to give you the answer. Questions on 5. The first part's important to Kirchhoff. I don't know what they're talking about with A and B. Yeah, I think Dr. Knight was maybe a little confused there. Let's go on to number 6. Then I think it's another Kirchhoff question, right? So we got to find number 6 was what are the magnitude and direction of the current in the 30 ohm resistor in that figure. So I need to